Okay, class, I want to finish up talking about this last bullet right here because I got cut off here at the very end. Um, all right, so if the degree of the highest degree in the numerator is larger than the denominator, then you are going to have no horizontal asymptote. Now, why is that? Well, because what's going to happen is this is going to be much bigger than this, and so it's never really going to approach anything. The graph in essence is unbounded because the numerator is just going to be always so much bigger than the numerator is going to be so much bigger than the denominator. So there is no horizontal asymptote. There is one little caveat that you should probably write in here, and this is that if m equals n plus 1, so in other words, they're separated by just 1 degree, or in other words, m minus n equals 1, you will have what we call a slant asymptote. And so you can, write a little note about that, and I can tell you how to find that. It's basically by doing log division of the two polynomials and figuring out the equation for the line that you're going to have as the result of the quotient of the two. But otherwise, but there is no horizontal asymptote otherwise. Okay, there is a slant asymptote only if there's a degree difference between the two. The other thing that you should know is the end behavior of the graph. Remember how we did end behavior in chapter 6? Well, remember how that worked? It was if the coefficient, right? You had a coefficient a sub n, right? If it was greater than 0, in other words, it's positive, or this is less than 0, then that's negative. And then we had even degree, right, and odd degree. And you remember how this all worked out? As if it was even degree and the leading coefficient was positive, I had both ends going up. If the leading coefficient was negative, I had both ends going down. If it was odd degreed and the leading coefficient, it was like goes down on the left, up on the right, and vice versa, right? Going up on the left and down on the right for odd. Well, this does the same thing, except now you're going to be comparing the two leading coefficients, and then you're basically crunching the numbers on the first set of terms, and whatever this degree is and whatever that leading coefficient is, the overall end behavior of the rational function is going to behave just like you learned end behavior earlier, the way that it would. Okay, all right, so now let's put all that together. You should have your book open to page 547. I want you to keep going back to that green page. Oh, one other thing I meant to tell you too is you can always find the y-intercept, right, of the rational function by putting x equals 0, assuming that, it's an allowable value. So you can always find the y-intercept, if there is one, by doing that. All right, so let's do example 1, and what we're going to do is we're going to keep that green box open, and we're going to kind of systematically go through it and then graph this function. All right, so the first thing that we're going to do, can I reduce the numerator and the denominator any further than they are? No. So they don't have any common factors other than 1, so that's the first thing. All right, number 1, then it says the x-intercepts of the graph are the real zeros of p of x. P of x being the numerator, right? So is there anything that's going to cause the constant 4 to become 0? No. So there are no x-intercepts. So there's no x-intercepts. Okay, so that's one characteristic of this. Then the second one says it has a vertical asymptote where q of x, in other words, the denominator, is equal to 0. In the real number system, is there anything that I can put in here that's going to cause this denominator, x squared plus 1, to equal 0? No, there isn't. So as a result of that, I have no vertical asymptotes. Okay, no vertical asymptotes. All right, number 3, we're going to figure out the horizontal asymptotes. Okay, so this is, what degree is the constant here? It's really x to the 0, right? So it's 0 up here, and it's 2 here. So is it top heavy, bottom heavy, or equal? Well, it looks like it's bottom heavy. In other words, the degree on the bottom is higher than the degree on the top. So what does that mean? So that means there's no horizontal asymptote. Okay? All right, so then the next thing you're going to do is you're just going to pick some x's and y's are going to just, and actually you can just get the table off of the calculator. And if you were to do this, okay, you would just key it in and then go second table. Well, it looks like, well, first of all, when x is equal to 0, right, that's my y-intercept. That's the other thing, too. What's my y-intercept? My y-intercept's where x equals 0. It looks like it's going to be, if I put a 0 in here, I'm going to get 4 over 1. So my y-intercept turns out, if I put a 0 here, this turns out to be 4, right? So I get 0, 1, 2, 3, 4. Here we go. All right, now so let's pick some, -2, -1, 0, 1, 2. Let's see what we get. All right, if I put a -2 in there, what do I end up with? So look at your table on your calculator. That's 0.8. And if I keep going further negative, it looks like it gets really, really close to 0, but it doesn't really pass. Oh yeah, wait a minute. It does have a horizontal asymptote. I'm sorry. Yeah, this is if it's bottom heavy. There. Well, what did it say? I've read the wrong thing. It is. It should be. There is a horizontal asymptote. It's y equals 0. Okay, let me just do that over. Yeah. Okay. No, I've gone too far. Sorry. I'm gonna keep going. Okay, so y equals 0 because it's m, this is m, and this is n. M is greater than n, so it has, well, it's the other way around. M is less than n. Okay, I'm getting my things. M is less than n. Here we go. All right, so that's y equals 0. So that's the first bubble. Okay. All right, because there is a horizontal asymptote. That's what I was looking at this, because this is approaching 0. And if I put a -1 in there, I get 2. And then if I put a positive 0, I put a 1 in there, I get 2. If I put a 2 in there, I get 0.8. And this is also looks like it's going off to 0 on the right. So if I plot these points, I get -2 is like kind of close to 1, but it's not quite there. And then +2, I'm up at 0.8 also. And then it seems to like go to 0. Then at 1, where am I? At -1, I'm up at 2. And then same thing here. So if I keep going and graphing these, I end up with a graph that looks kind of like this. Okay, and then you can, kind of look at it on the graph and you can see, yes, that's what we're going to have. All right, so, all right, that's example 1. All right, let's move on to example 2. All right, again, we're going to kind of go through the same kind of analysis that we did before. To make it easier to analyze, though, you do want to factor your polynomial out. Now, the top does not factor out the numerator, but the denominator does. This is a perfect square, that's a perfect square, that's a difference, right? Difference of two squares. So how does that factor? That factors like this, x plus 2, x minus 2. All right, so first thing, I cannot cancel anything out and simplify it. They are relatively prime. In other words, the only common factor they have now is 1. All right, so it says, now let's figure out the x-intercepts. They said the x-intercepts are whatever would cause the numerator to equal 0. Well, what is that? Well, if x equals 0, right, my whole numerator is going to be that. So it looks like I have an x-intercept at x equals 0, okay? Okay, so at x equals 0, I have an x-intercept. Okay, so I think I'm going to have that. Okay, now the other thing is number 2 says, let's check out the vertical asymptotes. Well, they said the vertical asymptotes are anything that would cause the numerator to equal 0. Well, I'm going to have to set each of these factors equal to 0 and figure out what that is. Well, what would cause, so I've got vertical asymptotes where? Well, at x equals -2 and x equals +2. So I have 2 of those. So if x equals -2, x equals +2. I have 2 vertical asymptotes, and you probably just want to kind of sketch those in right there. So you know your graph is going to hug those asymptotes, but get really close, but not cross them. And the same thing here on the right. Okay, so it looks like right now I got myself like 3 neighborhoods in essence. I've got a neighborhood to the left of this asymptote, one here in the middle, and then one to the right. All right, now let's see if do we have any horizontal asymptotes? All right, so the degree here is 2. The degree here is 2. All right, so the highest degree is 2. So what is the horizontal asymptote? Well, y, it's going to be the ratio of the leading coefficients, right? So what is that? The leading coefficients is 3 over 1, right? So I'm going to have a horizontal asymptote at y equals 3 over 1, or 3. So I might as well sketch that in. Okay. So that means that my graph is going to get real close to that y equals 3, but not cross it, get real close. And so, okay, so now we've got 3 different neighborhoods going on, and we got to figure out where we're graphing this thing. So you want to pick some x's to the left of -2, some x's to the right of +2, and then in the middle to see what you got. All right, so let's go ahead and we can put this in our calculator and then kind of come up with our, some x and y's. And, just to keep it sort of like with what the book is going, we're going to do -4, -3, -1, 0, 1, 2, 3, 4. Okay. Ooh, this is really a little bit cramped. 3, 4. Okay, so put that in your calculator, and then let's look at the table first, and then we'll try to sketch it. Try not to look at the graph to see if you can figure it out on your own. It's kind of fun. It's like a puzzle a little bit. All right, so 3x squared divided by, you should put parentheses there, parentheses, x squared minus 4, close parentheses, second table. All right, what do you see when you hit 2 and -2? Well, you're going to see error, right? Because that's where your asymptotes are, and that's where the function's undefined. So you're going to see error there. That's just kind of verifying your vertical asymptotes. All right, at -4, our graph is at 4. At -3, it's at 5.4. At -1, it's at -1. 0, it's 0. All right, because we said we had an x-intercept there. And then at 1, I've got a -1. I got another 0, and then I got, I need 2, I got error, 3, I got, I got 5.4, and then 4, I've got 4. All right, so let's start with this. It looks like what we're going to have is at -4, okay, 1, 2, 3, 4. I am going to be up at 4. 1, 2, 3, 4. So this is telling me this part of the graph is going to be up there in that corner. Okay, at -3, I'm going to be at 5.4. So that's 1, 2, 3, 1, 2, 3, 4, 5. A little bit less than. Okay. So just so you know, your graph is going to hug the asymptotes and not cross them really. So you're going to have something, you're going to have a hyperbola that does something like that. All right, then you got at 1, you got -1. So 1, -1. And then you got 2 is error. What do we get for +1? 1 is, oh, wait a minute, hold on. For -1, I got -1. Okay, and then a +1 also have -1. Okay, that's interesting. So it looks like my graph is doing something like that. And then at 3, I'm at 5.4. So it's going to be sort of up here. And then at 4, 1, 2, 3, 4. I'm up at 4, 1, 2, 3, 4. Oops, hold on, did I count this wrong? 1, 2, 3, 4. 1, 2, 3, 4. So there it is. So again, it's going to do something like that. All right, so I got to say these rational functions really kind of look funky when you start graphing them, because you have all these issues with asymptotes and stuff like that. So so that is our graph for example 2. And now example 3. All right, we're just going to do the same thing that we've been doing. But we gotta try to simplify our polynomial first. So let's look at the numerator. Is this factorable, the numerator? Yeah, because there are factors of -3 that combine into -2. What are they? Well, they're -3 and +1. So this factors into that. All right, and now I got x plus 4. Okay, and as you can see, I don't have any common factors, so that's check on that. Okay, so let's go back to our green box. It says the x-intercepts of the graph are the real zeros of the numerator. So what are the real zeros up here of the numerator? Well, so the x-intercepts are going to be where these equal 0, where x minus 3 and x plus 1 equals 0. So the x-intercepts are going to be at x equals +3 and -1. So I got a +3 and a -1. Those are my x-intercepts. All right, next thing. Number 2 is vertical asymptotes at the real zeros of the denominator. So what would cause the denominator x plus 4 to equal 0? Well, if x is equal to -4, right? So I have a vertical asymptote then at x equals -4. And I probably just want to go ahead and sketch that in. 1, 2, 3, 4. And I got a vertical asymptote right here. All right, now, let's see, do I have a horizontal asymptote? Well, this is squared here, and this is to the first power, right? Oh, this is one of those ones where you actually have like a slant asymptote. And the way that you would find the equation for that is you would do long division of this thing. So you guys remember how to do that? So x plus 4, this is a little added thing that I'm telling you it's not in the book. X squared minus 2x, they're kind of cool looking, that's why I like doing them. Okay, so x goes into x squared how many times? X, right? And then I got to multiply this through. This is x squared plus 4x. Remember, I'm subtracting. And it doesn't matter like about any remainders and stuff. You just are looking for the equation of the line up here. All right, so this cancels out. And then I have minus 2x minus 4x, right? So this is minus 6x minus 3. Okay, so x goes into minus 6x. What? Minus 6 times, right? And I'll get minus 6x plus, minus 24. But this doesn't matter. I'm going to have a remainder, and I get that. Okay, and this is going to go away here. Oops, let me see. How do I get this back over here? Well, that's interesting. Okay. Yeah, well, okay, I don't know. Anyway, so this is my line right here. X minus 6. That's my actual slant asymptote. So I have a slant asymptote, not a horizontal asymptote, at y equals x minus 6. All right, so how do I graph that? That's going to be 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. And I got a slope of 1 over 1, right? So I'm going to have a slant asymptote. It's going to look kind of like that. Right, and I'm going to be going through y equals to x equals 6 here. Okay, so I have a slant asymptote there. All right, so what you got to know then is, okay, so I got a slant asymptote. What else do I need to know? And then do I have a y-intercept? If I put 0 in here, this will tell me where I'm going to cross the y-axis. So that's -3 times 1. Okay, so that's -3 times 1, so that's -3, and then 0 plus 4. So they're saying I have a y-intercept at -3/4. Okay, so that's what that is. All right, now, here we go. So now you're going to go ahead and put this into the calculator. And we're going to get some values here, and I don't have enough room to write these down, so I'm just going to kind of list them out. But okay, so when you put it in the calculator, make sure you put parentheses around these things when you do it, okay? So we're going to do parentheses, x squared minus 2x minus 3, close the parenthesis, divided by parenthesis, open parentheses, x plus 4. Okay, second table. All right. Now let's go. We got to go. We got to go to the left of -4, right? So at -4, there's our error. At -5, we're all the way at negative. So we're down here, right? -32. At -5, we're off the graph, okay? And then we have our asymptote, um, and then as we get to as we get to that, it gets really, really, really close here on this side. And then, okay, let's keep going. At -4, we get this. At -3, though, okay, so -3, we're up at 12. Okay, so that's up here. All right, and again, this is, I think, only have 10 blocks here. So at -3, 1, 2, 3, I am up here. Okay, so it's doing something like that. And okay, and let's see, -7. Here, I'm going to go over here. I feel like I need a few more here. -7, I'm at -20. Okay, so still down there. At negative, do I even get, okay. Yeah, it seems to like -20 seems to get in here. I don't know that I'm going to see much of this graph. It's going to be down here. And I'm trying to see, the book is scaling this, so we're missing this part of the graph, I think, on here because of the scale. But it's going to do something like this. And then I'm going to have, it's going to do something like this. It's going to get real, on this side, just look at the table and you're going to put these in. These are kind of tricky, because you don't really, unless you kind of look at the graph ahead of time. But, but you're going to put it in there, and you just keep in mind that it's going to do something like, yeah, it's going to, it's going to come in here. It's going to do this. It kind of, just remember that your graph hugs the asymptotes. And so this has got kind of an asymptote down here. And I think, technically speaking, I think all this stuff is really happening down here. All right, this is very messy, but I've already invested too much time in this, so I'm going to leave it at that. So it's, so you're going to have to scale some of these things to see them. I think it's okay for you to look at them as you're graphing them, but just keep in mind that they're going to be different pieces and different things going on in different neighborhoods, and so you're just going to want to have that in here. You want to show that. So this is going to be like this. I think this thing's really in here, technically speaking, because I got this vertical asymptote going down here. I've got the slant asymptote going here, and this thing's down in here, and it's just not visible. It's off. It's kind of off the graph. Okay, so generally speaking, you put your asymptotes in. You try to figure out what's going on in between each of those neighborhoods, and that can be tricky without looking at it kind of ahead of time. All right, and I think that's it for now. I'll be back with the last video doing example 4.